This is in the notes here. It goes into quite long detail. What I'm going to do is just take a couple of aspects of the notes here, and then we'll do the examples and then the exercise. And maybe at the end of the exercise, in the last question, I might come back to say a little bit about more, fill in any gaps I mentioned in regard to the notes and say a bit more about it in general. But we'll go along on a need-to-know basis to start with, I think. So first of all, we ought to say a little bit about what is E. Basically, the observation here in this section is that all functions of a to a power of x can be written in terms of a single power. So you could write anything like this, like 4 to the x, or 8 to the x, or 6 to the x as 2 to a power. Now, how would you, here, this is the 2 to the powers we've got. We're going to claim that 4 equals 2 log 2 of 4. 8 is 2 log 2 of 8, and 6 is 2 log 2 of 6. Let's just see that on the calculator, shall we? 2 to the power log 2 of 4. We want to get the number 4 coming out there, don't we? 4. If we go back and we do 2 to the power log 2 of 8, then we get 8, which is what we wanted, and let's try 6, and we get the value 6. So that's true, these things are true. Now let's just verify that by taking logs here. So the log to base 2 of 4 here would equal the log of this, and this is log of 2 to a power, so using the power rule this would jump down to ground level, times the log 2 of this number. We know log 2 of 2 is 1, so this is clearly correct. Okay, so we just made that observation. We just checked it's true here. So all these things are true on the calculator and we've checked them algebraically. But suppose we want to just get it from the question mark, find out what value power of 2 is here. If we took logs on both sides to base 2, so this would be x log 2 of 4, wouldn't it? And this would be question mark would come down, it'd be log 2 of 2, which is 1. So again, you can see that the number here, we've just taken logs to base 2 on this side, and we brought the x down. And we did log to base 2 here, brought the question mark down, log 2 of 2 is 1, so that times 1. So I hope you can see that every which way round we go, we can see emphasized here that any power, 4, 8, 6, whatever number you want here, you can just write them as powers of 2s. And then you're going to get 4 to the x then, will be this to the x, won't it? See it? This to the x. Power u times, so you can write that as x log 2. Again, similarly, power u times, you're going to get x log 2 of 8 and x log 2 of 6. So there they are there then, and that's proven algebraically. So in calculus, rather than deal with these, we messing around with all different types of values of a, it's often preferable to convert it into one particular value. And I'm going to say more about e during the exercises, probably at the end, and why we choose e, but it's in your calculator. So if we have a look at our calculator, it's called the natural logarithm, and instead of writing log to base e, we often use the notation ln. So sometimes you might see me write log base e, and sometimes I might write ln. They're one and the same thing. And there they are on this calculator here. So if we do shift ln, which is the exponential of 1, e to the 1, we'll see what e is, 2.718, so on. It's an irrational number, so it carries on, ... and we've got the value here. So by the same token that we illustrated here for powers of 2, we claim a to the x is equal to e to another power of x, e to the kx. So what is the value of k then for any particular a? Let's take logs here, natural logarithms, because we're dealing with e to a power. We'll have x log a, won't we, here? X comes down, it'll be log a. The kx comes down, log natural logarithm of e, which is 1, as we know, because it's log base e. So if we did log of, let's just illustrate it, e to the power 1, we'll get 1. Okay, so that would be kx times log of e, which is 1, so that's just kx, and then that tells us that k must equal log a, mustn't it? Because a number of x's must equal. So there's our k value then. So we can write a to the x equals e to the kx e to the log a natural logarithm a of x. Much in the same way as we did the preceding example. See it? Where was it? Here, log 2 of 4. So it's e to the log e of 4. So e to the log e of a, the value. Okay, good, the value a. So if we want to write 10 to the x, all we have to do then is e log 10 times x. And if you tap log 10 in the calculator, ln 10, you get 2.30. And 6 to the x would be e log 6 times x, wouldn't it? Okay, good. So hopefully that's clear that we can now just deal with exponentials. So let's have a look at the examples. Right, let's have a look at these examples now then. Tap them into the calculator. First, e to the 2.3, that's 10 to the power, e to the 2.3. Doing it to a couple of dp, I think. 3 significant figures. 9.97 is the first one. And then e to the minus 1.4. Minus 1.4. 0.247. And ln natural logarithm of 32. ln 32. 3.47. And we've also got, ln 32, let's try that again. ln 32, 3.47, yeah, that's what it is. And ln 100, natural logarithm of 100, 4.61. Okay, let's solve these equations and then take logs to base e, or write this in logarithmic form. Remember the e swings down to be the base number, and the x squared minus 4 drops down to ground level, and it's log e of 1000. So x squared equals, move the 4 over, it's ln e of 1000 plus 4, and then we square root, don't we? So x will equal the square root of, so it'll be plus or minus ln natural logarithm. I don't need the e there because I've just written the natural logarithm. That's log base e. 1000 plus 4. So let's have a look at that. So the square root of natural logarithm of 1000. Close the natural logarithm plus the 4, all in the square root, equals 3.30 to 3 dp, plus or minus 3.30. Okay, good. Next one. So let's scratch this and we'll do the next one now. Okay, so unwrap this log, the e swings down and hits this in the air, so 1 plus 3x then will equal e squared. So the 3x will equal e squared minus 1. So x will equal e squared minus 1. Move the 3 from times on this side to divide on the other side. So it's e squared on the top minus 1, that's on the top, divide by 3, 2.13. That was the 3 decimal places, wasn't it? Next example then. Make x the subject. Write down this as log, in log form, log e of y. That's log base e, that's how we write it, is 3x. So the x will equal log y over 3, or 1/3 ln y. This one, move the 1 over. 4e to the minus x. Now move the 4 underneath. So y plus 1 all over 4 is equal to e to the minus x. Now write this in log form, ln log base e of y plus 1 over 4. That swings down to be the base of the log. The minus x drops down to level, ground level. So x is equal to minus ln y plus 1 over 4. Okay, good. Next one, make x a subject, so bring the 2 over, y plus 2 is equal to ln x. Unwrap the log, so the base e swings up, hits this stuff in the air, e to the y plus 2. Next one then, move the 3 down, y over 3 is equal to ln 5x minus 1. Now we can unwrap the log, e to the y over 3 then is equal to 5x minus 1. Move the 1 over, so 5x will be left on its own. That will equal e to the y over 3 plus 1. Move the 1 over, and then divide by 5. So it's e to the y over 3 plus 1 over 5 is x there. Now let's look at the next example now. We've got a cup of coffee. Room temperature is 20, and theta is the temperature above room temperature. E to the minus 0.02t. Okay, good. So there's the formula. Theta is temperature above room level. What's theta equal to then when t is 10 and t is 30? So it's 80 e to the minus 0.2t. T equals 10, t equals 30. Let's put it in our calculator. 80 times e to the minus 0.2 times t, which is 10 on the first instance. 10.83 degrees centigrade. Not too sure about this. Let's have a look at that again, see if I've got it right. 80 e to the... I know where I've gone wrong. It's minus 0.02, isn't it? There. So be careful there. So I've written it down wrong as well here. 65.50. 65.5. 65.5. Theta is, the model is 0.02, so I need to squeeze a 0.02 in there. 0.02t. When t is 30, just go back and change the 10 to 30 then. Tap that in. 43.90, 43.9 degrees centigrade. What's the temperature then? And the temperature when theta is 30, so we better rearrange. So move the 80 underneath. Theta over 80 is equal to e to the minus 0.02t. Now write the log form. The e drops down, natural logarithm then of theta over 80. And this power term drops down to ground level. And now we can find the temperature. So the temperature will equal then, move the minus 0.02 down, so you got log of theta over 80 over minus, which we can put at the top, 0.02. Now if you want to write that tidily, you could do 1 divided by, because there's a 1 on top, 0.02, and see what the number is, 50. So we could bring that up just as we do with fractions, minus 50 ln theta over 80, and that does look easier on the eye. So when temperature is, when theta is 30 then, put it in. This is when theta equals 30 degrees C above room temperature is the measurement. Minus 50 times the natural logarithm. I need to get rid of that ants thing. Theta, which is 30, divided by 80, close bracket.